Okay, this lesson is going to be on isotopes and atomic mass, or average atomic mass. And the first thing we're going to talk about are isotopes. Okay, so you've probably heard this term before, possibly in physical science, but basically what this is saying is this is where we're disproving one of Dalton's postulates, where if you remember, Dalton said all atoms of the same element are identical. Well, previous research has showed us that we can have different elements that have different numbers of neutrons, which is what we're going to call our isotopes here. Okay, so isotopes, what does it mean? It's the atoms that have the same number of protons. Why? Because the proton defines what element we're talking about, or the atomic number, but different numbers of neutrons. Okay, so we're talking about a variation of mass numbers for a certain amount of atoms. Okay, so the primary example here that I'm going to use is the three forms of hydrogen that we can have. We can have hydrogen 1, hydrogen 2, and hydrogen 3. Now, if you remember from our naming, the number past the name indicates its mass number. Okay, so if I was to look at this hydrogen 1, obviously hydrogen has one proton always because hydrogen's atomic number is equal to 1. Okay, it has one proton always, defines hydrogen. Okay, so in this case, hydrogen 1 has one proton, and if it's only 1, that means 1 minus 0 is going to give me a mass, or 1 plus 0 is going to give me a mass number of 1, which indicates that I have 0 neutrons and a mass number of 1. Now, you see here that I have one electron, which is negatively charged, so that's what that negative charge means. So if I was to write this symbol, it would be hydrogen 1, 1. Okay? Hydrogen 2. Now I'm adding a neutron to the nucleus. Okay? So protons don't change for hydrogen. Now I have one neutron, which ups its mass number to 2, and I still have one electron, which neutrals out that 1 plus charge inside of its nucleus. So my symbol here would be H2, 1. And then hydrogen 3, I still have that one proton, but now I have 2 neutrons to get a mass number of 3, and still 1 electron. So my symbol here is hydrogen 3, 1. Okay? So that's just an example of mass number based off of 3 different isotopes. Now, you've probably heard, you've heard the term mass number. Mass number is specific to protons plus neutrons, okay? That's not the mass that we have on the periodic table, okay? The mass that we have on the periodic table is called the average atomic mass, okay? Or atomic mass. So for whatever reason, these notes didn't get put into your stuff here, so I'm going to kind of go rogue here, so it's important that you have this information, okay? So atomic mass, or sometimes referred to as average atomic mass, okay? It's the weighted average of the atoms in a naturally occurring sample. So like if I was to take a sample from Earth, that one sample is going to have multiple isotopes within that sample, okay? And then the weighted average reflects both the mass and the relative abundance of the isotopes that are present in nature, okay? So what does that mean? It means that I have to take into account the mass of the isotope and what percentage of that isotope occurs in nature, okay? So to calculate, or if I was to look up, because that's what these examples are, if I was to look up the average mass of carbon, if I was to look on the periodic table, the average mass of carbon is going to be 12.01, okay? So since I have a decimal here, this isn't going to be mass number because I can't have decimal protons and neutrons. So the average mass is always the decimal number on the periodic table. So in this case, carbon is 12.01. I don't know why I didn't write 1. Gold is 196.97. And then if I was to look at uranium, it would be 283.03. Okay? So that's the difference. Average mass is not mass number. Average mass is the mass of all isotopes and their percentage available in nature, okay? So if I was given each isotope and its abundance in nature, can I calculate the average atomic mass? Well, yes, hopefully you can, okay? So let's look at the equation that we're going to use to calculate this. Atomic mass is going to be equal to the relative abundance, so how much it occurs in nature, times the mass of the isotope. Most of the time this is going to be the mass number, plus the relative abundance of the second isotope times mass of the isotope. And you could keep going. I could say plus the relative abundance of the third isotope plus its percentage in nature, which would go back to our hydrogen example from the previous page. Okay? Your final answer should be closest to the mass of the isotope that occurs most in nature. Now that makes sense. If I have something that weighs 6 and I have 75% of it that occurs in nature, I would expect my average mass to be closer to 6 than whatever percentage was for the other mass number. Okay? So let's look at an example. So I'm going to do this two different ways. I'm going to calculate it by using its mass number and this thing called AMU, which is the atomic mass unit, okay, which is going to be 1/12 of the mass of carbon, which is roughly 1 proton, okay? But we're not going to get too heavily in that, so I'm going to do it both ways here to show you in case you're given one or the other, okay? So the first thing I'm going to do is I'm going to rewrite my formula and then plug all the numbers in, okay? So I'm going to do atomic mass is equal to the abundance of 1 times the mass plus the abundance 2 times the mass of 2. Okay? Now it's important to note here, I'm going to be given abundance in percentage. I need to take it out of its percentage form to calculate atomic mass. So in this case, I'm going to swipe twice to make it 0.99985. And the mass that I have of hydrogen 1, that's the abundance that I have for hydrogen 1. So that's mass 1 plus the abundance, so I'm going to go 1, 2. So it's going to be 0.00015 times the mass 2. Okay? Now if I plug this into my calculator, I should get, so 0.99985 plus, I get 1.00015, okay, AMU. Now, if I was wanting to check my answer, I would go to the periodic table to see if that number is close to what hydrogen's is, okay? Now these periodic tables are rounded to 2 significant figures past the decimal, so this says 1.01, okay, which we're a little off here. But since I have this AMU here, I'm going to now calculate it to see if I can get closer, okay? You're not always given AMU, that's why I wanted to do it both ways. Okay, so let's look at this guy. So now I'm going to say, I'm going to do it again. So my percent abundance is 0.99985 times 1.0078 plus 0.00015 times 2.0141. Now I'm going to expect my number to be closer to this 1.0078 because that's my higher percentage, okay? My way higher percentage. So let's plug that guy into the calculator. And I get 1.00795, which actually gives me that 1.01 that my periodic table talks about. Okay, so what is this saying? This is saying that my relative abundance of a hydrogen that has a 1.0078 AMU is going to be closer to the mass number that's on the periodic table. Okay, so that is isotopes and AMU and how we calculate the mass that we find on the periodic table.